Well, good morning, everyone, and welcome to RISB's most current RISB Masterclass webinar. Today, we are looking at innovations for risk reduction and driver well-being. We have some great speakers here today, Dave Sheehan and Julian Pollard from IDS Corporation, who I will introduce shortly. But before we get underway, I would like to acknowledge the traditional custodians of the land of where we meet today. For me, I'm in the suburb of Baldivis in Perth. So that's the Binjarrab, Wudjuk, Noongar people. And I wish to pay my respects to their elders past and present. I also extend that respect to all Aboriginal and Torres Strait Islander people with us today. Now, level crossings are a pretty common sight across Australia, both in metropolitan and regional areas. We have over 20,000 level crossings here in Australia, all of which require road and rail authorities to manage the risk associated with these locations. Now, over the years, RISB has supported the rail industry by developing a number of documents regarding level crossings. This includes AS 7658 level crossings, rail industry requirements, and the guideline for safe operation of restricted access vehicles across level crossings. There's also the well-known Australian Standard Series, AS 1742, which provides significant information on level crossing design and operations. Further, RISB continues to support the National Level Crossing Safety Committee, as well as the National ALCAM Committee, who provide standardised assessment for the process of level crossings around Australia. Now, it's a bit of a sobering fact that in the 2023-24 financial year, the Office of the National Rail Safety Regulator, ONSA, reported 7 fatalities at level crossings. There were also 39 level crossing incidents and over 450 reported near misses with vehicles. So whilst these numbers are coming down slowly in some areas, this certainly suggests that a lot more work needs to be done to reduce the risks associated with train-vehicle interfaces. Now, ideally, the ultimate goal, of course, is grade separation through the use of bridges and tunnels, but this isn't always practical. New technological approaches also need to be considered, and that's what we're here to look at today. I'd like to welcome now Dave Sheehan and Julian Pollard from IDS Corporation to talk about the work they've been doing in this space. Now, Dave Sheehan has been with IDS since 2011, heading up the commercial division of the aeronautical data management for civil and defence sectors in the APAC region, which includes some rail work in his portfolio. Dave's background is in sales and business development and a long history in software and technology, including complex technology and electromagnetic solutions for radars. Julian is an experienced aeronautical and mechatronics engineer with a unique perspective, having overseen the design, manufacturing and successful field deployment of complex technologies over the last 8 years. Julian is the lead engineer for the LXOD projects for both Rio and the APAC region. Now, I'd like to remind everyone, if you have any questions, can you please go to the QA section of this presentation and drop any questions in that you would like to be asked. I'd like to ask of Dave and Julian, and I will present those questions to them both at the end of this presentation. So that's enough from me. I'd like to now hand over to Dave.
Thank you, Chris, and appreciate everyone for joining us, and thanks for such a great introduction. And as Chris has highlighted, this innovation for risk reduction and driver wellbeing, but we do encompass any workers in and around the rail and also the public safety. So the presentation explores how radar technology may be applied to enhance safety and reduce stress and lower risk of incident at level crossings for rail workers, emergency workers for that fact, and the public. So welcome to the webinar on enhancing level crossing safety with and discussing how radar technology may support that. Today's focus is improving safety and mental health for train drivers through innovative solutions. By innovative solutions, I am referring to radar as the technology and probably just the next jump up to what is currently available. And why it matters is that level crossings are a high-risk area with significant impacts to train drivers, the public, emergency services, depending on what type of incident it occurs. And with the agenda today, we'll have a bit of a look at how the current state of level crossings are, the benefits of those, how we may be able to align the radar technology to the ALCAM assessment tool, which is obviously a critical tool. And at the end of each slide, I'll propose just a thought-provoking question that, or a question that may questions from the audience. And I'll start off with the first one: is that how can we leverage technology to enhance safety and mental health for train drivers? So some of these references that I'll talk through here about the current state of level crossings and that have come from April 2025 of TrackSafe and some information from ATSB, and Chris provided some of those statistics prior. So level crossings across Australia, we have around about 23,000. Some of those, we start to look at the first tile there on the left, which is where we look at what I call or refer to a bit of a stack as well. So we talk about basic, where there's basic level crossings where there's no control. There's a very low cost implication for those, but there is obviously the high risk because it's self-assessment by the road user. You know, can I make it in time? And you know, sometimes there is that challenge that they try to do that, and as we've found, sometimes they don't, and there's no automation for it. So as per the ATSB and TrackSafe data, with only 21% active using boom gates or lights, most rely on passive signage, highlighting risks mostly in the rural locations, and moving through to rationalised systems, which we talk about in the third tile there, may change that. When we start talking about the basic, standardised or rationalised and dynamic, and then dynamically rationalised is how we phrase it. Here is that the rationalised obviously has more technology in it. You know, there's the CCTV cameras, there's the boom gates, there's the wigwags, there's signage, and a whole heap of systems there to try and help stop that. And then with the collisions at level crossings, which do contribute to rail-related fatalities and injuries, we then look at that standardised and rationalised with enhanced warning or human intervention with the CCTV. From 2016 to 2024, TrackSafe reported 28 fatalities and 156 injuries from train-related or vehicle collisions, with several deaths and injuries involving pedestrians. This may not necessarily be associated to level crossings, but there are near misses in most circumstances and incidences. With nationally, there's been over 8,300 near hits occurred, which averages around about 900 odd a year. And when we progress to the dynamic side tile there, so the second last tile, we start to look at how do we how does that reduce or lower the risk, because it's actually real-time data. So it's 24/7, 365 degrees in all weather conditions. It is cost-effective compared to things such as the upkeep of rationalised level crossings, or then compared to obviously grade separation, where we have the road users having their own lane and rail having their dedicated rail line. When we progress to that full automation, this may slash these numbers as it provides the real-time data that I was saying, and that way, with that real-time data, you can actually make better decisions. And due to the unpredictability or forewarning that train drivers may face with the potential trauma or from incidences at level crossings, it is about the high unpredictability at the passive crossings with no warning, such as reliance on user compliance. And with the ATSB research showing that near misses and collisions do disrupt the focus, they lead to stress. And then that's where you have some of the human intervention, which partially addresses but doesn't fully resolve those, or that helps with that. When we start talking about the mental health concerns, increased stress, anxiety, and risk to PTSD for train drivers, a possible solution of things like incidences where person under train events cause severe impacts. There is a percentage of drivers developing PTSD, noting that thousands of annual near hits amplify anxiety and absenteeism. And advancing through to the dynamic system protects rail workers, public and emergency services workers' well-being by having something that allows them to stay a little bit more in control or having predictability. And in closing on that slide, what are your highest or primary challenges and risks associated with level crossings today? Now, when we start looking at and comparing the technologies, we do look at fairly basic of signage, and then which is fairly robust. You move into LiDAR and then obviously radar. And in the left column there where I've got aspect, I like to refer to it as a stack. So we have the technology, what technology is available, and at even the rudimentary side of it, you can call signage as technology, but it does have obviously its purposes. Then you look at the application technology and how does that support the technology from the application side. You then have the data output. Obviously from the signage, there's really no data output whatsoever. It does rely heavily on human observation and compliance. You move through to things like the LiDAR, where it provides detailed imagery. It may be slower and less dependable in real time. But then you look at the radar, which does deliver real-time data for instant warnings and smart decision making. But then you have a look at the benefits outside of that, which is improved safety from a radar point of view. It will reduce the risk because you have the real-time data of what's going on there to then be able to hopefully implement some other solutions to prevent whatever's causing the incidences if they're regular, and enhanced situational awareness. You move through to the performance side of it. So, and what Julian will be talking about in one of the slides there is one of our trials that we're looking to do. And that's particularly relevant in the fact of bull dust out in the Pilbara region, where there is a lot of dust, but there's also a lot of environmental stuff that's going on with things in the air and so forth that can affect lenses and so forth. So with the radar, it operates in all sort of weather conditions. We've had this operating in snow, we've had it operating in heat, we've had it operating in low visibility, fog and so forth. And obviously at night time, it doesn't have to rely on a lens to be able to see through the night. It works on the radio wave, so it's very effective. And then the robustness of it. The radar operates on radio waves to detect the objects and the movements. The application side of it is for detecting vehicles, pedestrians and obstacles at crossings. And I'll just caveat that by saying that it's not so much that the radar says that, hey, it's a human on the track or a vehicle or a llama for that matter. It actually just then through the understanding of the output, the engineer or the worker that has been trained on the system will then understand what the object is, and then they can report that back. It does provide the real-time data, as I was saying earlier, for early warnings and decision making. And in early warnings or decision making, hopefully be able to have the driver slow the train down or bring it to a stop. The benefits obviously are improved safety, reduces the risk, provides enhanced situational awareness, and operates effectively in various conditions, outperforming some traditional sensors. Now, if you had access to real-time data from radar technology, how would it assist you in your organisation to transform level crossing safety? Now, some of the benefits obviously to the drivers are early detection, hopefully enables preventative actions, enables preventative actions, reducing accident risk. And with technology such as the radar, drivers get real-time alerts, or operations centres get real-time alerts to obstacles, allowing for hopefully quicker actions to, as I mentioned in the previous slide, slowing the train down or bring it to a halt. Obviously, in a lot of cases, we're aware that that may not be possible. However, the mental health side of it is advanced technology reduces stress and anxiety. And I'll basically bring up the, how does that kind of, maybe that's the question you got in mind. Well, how would that do that? And I just take the scenario fairly simply that, we have our flight or fight response. In the case of if we're pre-warned about something is going to happen, we're obviously mentally and physically better prepared. Whereas if, we have a spouse or a child that might be going to frighten us, or, we have a phobia of spiders or snakes, but they suddenly appear, our reaction is far greater. Whereas if, someone tapped you on the shoulder and said, hey, look, there's a snake there, or, someone's about to jump out and scare you, you are better prepared, or you avoid it. I mean, obviously a little bit hard with the train to avoid, but as you imagine, if the train driver is aware that there is something on the track, they can better prepare themselves, they can better prepare the passengers by a notification, and allowing them to physically prepare themselves or mentally prepare themselves, which hopefully with an advanced system like the radar detection, it'll cut down on the unpredictability that drivers face across crossings and help lighten the constraint of the mental workload. As we've seen from the earlier data and mentioned by Chris as well, is that near hits and PTSD risks, these provide real relief by creating more predictable outcomes and less anxiety, hopefully, in those types of situations. So there'll be proactive awareness, and information about level crossings allows better preparation in real-time prediction, and the radar provides situational data on crossings activity and providing, which will hopefully improve reaction times. Therefore, it may then reduce trauma reduction. Fewer incidences mean less exposure to traumatic events, and empowerment to the drivers who feel supported and more in control. By the reliable technology, drivers can shift from a reactive to a proactive role, and studies can highlight how stressful events disrupt performance, but innovations restore control. In what ways can advanced warnings or systems improve the well-being and performance of train drivers and passengers? With the next slide, I'll now hand over to Julian, who was obviously introduced there by Chris as our lead engineer for our LXOD. You may hear him say next slide, so that's my cue to move on. So I'll hand over to Julian.
Thanks, Dave. So ALCAM is a critical tool for assessing and prioritising level crossing safety. Radar technology may align with ALCAM to help improve overall level crossing safety. Radar technology allows for real-time condition monitoring, and it allows you to detect traffic and pedestrians. It acts as an early warning system, reducing incident severity, and even in some cases, reducing incidents completely. Integrating radar data can improve ALCAM's effectiveness. It ensures safety improvements are data-driven because you can conduct data-driven analysis. By implementing radar technology with ALCAM, how would it enhance your approach to safety assessments? Next. So I'll now get a little bit into the technical side of it, not too deep, but just a little bit to pique your interest. But sorry, got to move with you. There we go. Yeah. So the radar systems like the LXOD are set up on crossings to reduce risk. They basically are radars that detect when an object is on the detection zone and gives you a signal whether it's occupied or free. So a typical setup, we usually use 2 radar heads, but this depends on how complicated the crossing is. So up the coloured picture up in the corner here, we can see quite a complex crossing. We've got a Y intersection across 2 different sets of tracks here, and they achieve this by putting in 4 radar sensor heads. The detection range varies. So for train protection or vehicle detection, we've got a detection range of 25 meters, and people protection or people detection, we got 15 meters. The detection zone occurs in a field of view of 120 degrees. There are a number of things which can hinder the ability to pick up an object. If you have a look in the bottom corner here, we can see when there's not flat ground to get on, we can miss returns like around corners of stuff. Also, you can get false detections from reflections off a wigwag or a sign. So these detections might bounce off the wigwag and then back into the detection area, giving you a false positive. So we compensate for this by actually blocking out troublesome areas from one radar sensor. And as long as there's another radar sensor which can see that area, then it's completely fine. So up in the picture in the right, we can see a ground plan where we have the dotted red lines indicating the scan area of the 2 radar sensors. And we also have the dark blue and pink/purple detection zones. So the blue is the main crossing detection zone, and the pink is the close to barrier detection zone. We have quite a few different detection zone types which have their own algorithms to help enhance your results. So we can pretty much cover any type of crossing. So considering the complexity of crossings in your state, how many radar sensor heads would you need? Thanks, Dave. So there's 3 main components of the LXOD system. We've spoke briefly about the radar sensor head itself, but all the radar sensor heads on a crossing are connected to a control unit, which manages them and then sends the signals to the signaling system. So these are isolated from the internet and have a really high SIL rating, safety certification. But we also include a diagnostics unit. And the main purpose of this diagnostics unit, which is not SIL rated, is to assess incidents after they happen. So we can view this through locally, like at the actual crossing, or in real time through a web-based software using a mobile internet connection. It has customizable inputs, so you can bring in whatever sensor data you want and customize what alerts you want. So you might want an alert with particularly bad weather, an incident, or any faults in any of the sensors that you have connected. And a general example of this situation is the picture we can see here. We can see the radar sensor in the middle tile has picked up a target. They'll then go and find the timestamp of the report, and they roll all the sensor data back to that timestamp, and they can actually view everything that's going on when that target was found. So here we've got CCTV cameras that are capturing the cyclist going over the crossing after the barriers are down. We've also got one camera that's focusing on the light to see if it was working properly. And it's also integrated with weather, so we can see there's no rain, there's no snow. And often they also link it with red light cameras. So if a car runs a red light, you can see that as well.
Oh, sorry, Julian.
That's all right. I was changing as well, forgot to keep up. Yeah, so what other sensor information might be beneficial to include in a diagnostics unit system to generate a comprehensive assessment of an incident? Thanks, Dave. So now we'll dive into a few use cases. The main one that we'll go through for Australia is the work that we're currently doing with Rio Tinto. So Rio Tinto is looking to upgrade their current level crossing obstacle detection system with the LXOD, mainly due to its reliability, low maintenance, and high safety certification. So the picture on the right here is showing the site that we're working with in the Pilbara. So we can see it's a nice and easy site to start with. Not a lot of things around to cause issues. They also have their current obstacle detection system there, which is great for running the trial. And here we can see the initial ground plan of the site. So with every site, you need to do a ground plan. Where do you want to detect? Where are the barriers? Things like that. So we've got the red and the blue indicating the two different radar sensors, and the line in the middle indicating the bore site. And when you are installing the radar sensors on a site, they do need to have reduced vibration, because if it's vibrating too much, you will get false positives all the time. And so for this site, we're initially running tripod setup just for the initial test, which is if you're doing a short test, a tripod setup can be okay. But then we're fixing in piles to make a really sturdy system. Thanks, Dave. Oh, no, actually, yeah, good question. What other sensor oops, no, sorry. So where might a trial site be suitable in your state? So I'll now pass over to Dave to continue.
Thanks, Julian. So we're sort of coming to fairly close to the end of the slides, but with some of the use cases that we have, which is a significant rollout with Network Rail. Through Italy, we actually have hundreds of the sensors. They are slightly different, and I'll go into those in a second, but typically in the uses in the UK, the radar detection system is on double barrier crossings. If a target is detected inside the barrier after it closes, then the barrier can then be opened to let the trapped target out. Now, an overview of about the IDS appointment was selected by Network Rail to have a 5-year framework agreement. It established for the radar as the next generation obstacle detection replacement of current systems in most cases, but it also can work in conjunction with other technology as well. In most cases, it's quite easily to adapt and integrate in any case. The strategic alignment is supporting the Network Rail's safety enhancement goals, with innovation focus being advanced level crossing protection with cutting edge technology. Something that, as Julian, I think, mentioned there, that it is SIL 1 and SIL 4 rated. So it is highly part of the safety integrity level. And then the problem statement that Network Rail requirements was seeking advanced obstacle detection to ensure as low as reasonably practicable ALARP safety principle in at critical level crossings, and the key priorities being high reliability, minimal maintenance, and optimal cost of efficiency. And when we talk about minimum or optimal operations, so it is a 15-year between mean time fail, which is exceptionally high. And then the challenges is with the legacy systems, older LiDAR systems and combos suffering from part obsolescence and the regular upkeep and demands. And then we have the upgrade rationale is between replacing outdated tech to enhance overall rail safety and operational sustainability, with the proposed solution being to implement the level crossing obstacle detection radar for automated clearance checks, with the core functionality being to ensure that level crossings are obstacle-free before a train proceeds, which is obviously quite important. And the key benefits to enhance safety through reliability, real-time verification, with the operational impact to prevent accidents by integrating with signalling systems. You'll see from the top right image there is a 4-quadrant, so it is obviously different to what we have here in Australia, but very adaptable for the Australian conditions. As part of the trial through UK, this did start back in 2020, 2021, and then through obviously COVID, there were a lot of challenges. But one of the sites, to point out, is the Nether Poppleton at York. That was actually a rail corridor. They found that an interesting trial site because there was actually a lot of pedestrian activity, even though it seems like it's in the middle of nowhere. But that type of real-time data helps then put in or implement solutions such as gates, fencing, and so forth. So it doesn't necessarily have to always be, I mean, predominantly it's level crossings, but it can be through rail corridors. So if a radar system like this is implemented on Australian crossings, would this make them safe enough to introduce double barriers? And moving through to our Italian cases, like I said, there's around about 400 or 500 sites that have the radar. And as you can see, in Italy, it's a little bit unique in some of the cases, with the top right one being livestock, just crashing through the barriers there. Although we do have our lovely cattle grids in Australia, which are very effective. And then you have the pedestrian side of it. Again, all of this is time stamped, so that there can then be hopefully other types of preventative measures put in the case, whatever the authorities may feel necessary to prevent these sort of things. And then in the bottom left, you have the overview of what the system may look like. Now, the actual post there, what Julian was referring to about the rigidity of the post and less vibrations, that's also then compliant with the SIL 1 for pedestrian detection, so that there's less vibrations, and that's why that we need it so robust in those circumstances. And considering the existing implementation in other countries such as the UK and Italy, while different in the setup of barriers, markings, and etc. of how it's set up, what benefits do you see by implementing a radar in Australia at level crossings? And moving through to our final slide here, radar technology offers a promising solution for level crossings and for a trained driver and rail staff and public well-being. As we've sort of outlined there, to be prepared for something or forewarned about something, we can better prepare ourselves. And a possible alignment with the ALCAM ensures technology's existing assessment frameworks, and continued innovation and adoption of new technologies are crucial. We feel obviously to keep moving forward and enhancing the level of safety at the crossings, and encouragement for stakeholders to explore trial radar solutions and how they can be fit for purpose. And I guess, what steps can we take today to ensure a safer tomorrow by implementing such technologies? And back over to Chris.
Great. Thank you very much, Dave and Julian. Very interesting presentation. Greatly appreciated. I do have a couple of questions for you. The first one that I'll ask is, we've got a few that have been posted up, so I'll start with those. The first one here was for the trapped target. So you talked about trapped targets there around the 4-quadrant level crossings. Does the object need to be moving for the radar to detect it, or can it be stationary?
So it kind of needs to be moving. If you're talking about the child on the ground, they actually can detect the difference in the child breathing. But if there is like an object that fell off the back of a truck because it isn't in the original, like the, I guess the background scan, that will still come up as well.
Okay, so if a car, say, stopped in the middle of the crossing, though, it would still detect that car stopped in the middle there.
Yes.
All right, great, thank you. Another question we've got here is for crossings that have been trialled and used, what is the incident rate comparison between pre and post commissioning of the trials? Have you got any data on that?
No, that's a great question, but we'll try and find what we can out from our studies in the UK and that sort of thing. So if we can keep that question aside, and we'd love to come back to whoever that is and provide those answers.
Yep, we can certainly do that. So thank you very much, Louise, for the question. Regarding the SIL ratings, can you double up radars to increase the probability of detection, or are non-detections common mode correlated?
Yeah, so to get it to the SIL rating, you must always have a radar covering a spot. If we need to block out an area that's like coming up as a false positive, we must have another radar that covers that area.
Right. Yep. I understand. Thank you very much. Another question. I've got a couple for you myself. So we've talked a lot about the use of the technology for level crossings, but have you considered the use of the technology for other purposes? So, for example, event railway stations, so stations next to stadiums, etc., where you go from just having very few people at the station, then all of a sudden you've got tens of thousands of people milling all over the place. Have you sort of looked at other uses of this technology to detect people on tracks where they maybe shouldn't be?
Yeah, for sure. And that was the one that I showed the image of the rail corridor. So obviously it's a very long line of track where there is pedestrian moving, where they've had near misses of pedestrians, going over there or noting by security guards or whatever it might be. So yes, for sure, that is something that we can apply the application to in the right setup and the configuration and understanding the area, but it can be applied to those sorts of scenarios.
Oh, excellent. Yeah, because I think there'd be a lot of opportunities for those sort of incidents where it may not be necessarily a level crossing, but there are a lot of people in the area for particular events, for example. Got another question here. How are you planning to communicate with the train driver when there is an obstacle?
So we don't actually communicate with the train driver. We only output is the crossing occupied or not, and then it's up to you to figure out what to do.
Okay. Yep. So that sort of leads me on to my next question. As you may be aware, there is now an agreement nationally to implement ETCS across the National Interoperability Network. So how would this system, do you know if this system could actually integrate with ETCS as it's rolled out here in Australia?
Yeah, that's a tough question to answer right now, because we'd have to really understand and sit down and know what that is exactly about and how we can integrate with it. I mean, it is possible, because we integrate with most systems in any case. So, but understanding what the framework is and the technical back end and all that sort of thing, we'd be able to just work through that. It's it's only fairly new for us. So,
all right, no problem. Thank you. Now, just having a look through here, there was a trial of radar units at Laverton in Victoria in 2014 at a gated crossing. The Victorian government would accept the radar and correlated visual imagery for prosecutions of drivers, so they wouldn't accept this. Is there any jurisdiction that allows prosecution based on radar and visual imagery that you're aware of?
No. That's a curly question. That's a new one, but no.
Not that you're aware of?
Yeah,
no.
I'm not aware of it, but I do know that in the UK it is linked up with the red light cameras.
Okay, yep. Which is a prosecutable way, I suppose, of getting the people who are doing the wrong thing. So, yeah, so obviously it's certainly possible.
Yeah. I could say like anything. It's like anything. If you've got the evidence or data to back it up, and then I guess why not?
Yeah,
should be able to support it. So,
so an interesting question here. Has this technology ever been considered for the activation of level crossings? And if not, what do you think some of the limitations might be?
That's a brilliant question.
the activation of level crossings. So bringing them down.
So it's more, I'm not sure how you'd particularly use that, but it's an interesting thought. Whether it's instead of looking at the level crossing, but now you're actually looking at the approaches, like trains on the approach. So when a train is on the approach, the radar would actually trigger the level crossing rather than traditional track circuitry.
Yeah, so currently it is the other way around. We will, in the UK, we take the signal saying that the barrier is now down, check the crossing, and then we check the crossing and then send the signal back, and they'll actually red or green light the train to proceed. So if there is a target in there, like Dave was saying, it will lift the barrier back up, let the target go out, barrier will come back down, check again, and then give green light to train. So it's kind of like the barriers coming down is what starts the process currently in the UK.
Oh, thank you. I've got a question here, and adoption of new technologies is always a big question here in Australia. What do you see as the key technical and regulatory steps required for broader adoption of radar systems in Australia? And do you see that in a way that how RISB might be able to support that?
Yeah, so look, I think the first thing is doing the trials to make sure that it's fit for purpose and getting that data and leveraging what we've done overseas and other trials that we're doing in I think it's Belgium and Germany, and then obviously the UK. Italy's been running for a long time, but getting set up, because obviously we need regional infrastructure manager to run those, to sign off on those and provide the evidence that it's safe and can do what it needs to do. And hence with the trial with Rio, being able to have that availability to do that. Trials obviously take time, 6 to 12 months, and then proceeding to the evidence that it's fit for purpose and then can be rolled out. So, definitely being able to do that. What was the second part of your question there, Chris? Sorry.
So do you see a role for RISB in assisting you in the adoption of these systems?
Look, can't see why not. I mean, it's working with all stakeholders in it, and certainly RISB are a key stakeholder in that. So looking to see how we can actually support for what you do in industry would be of a huge benefit to be able to have that adoption, because I mean, coming from the aviation background that I've supported for a very long time with the company, and then moving into the rail in the last 5 years, I thought aviation was antiquated with the way that they operate and implementing new systems and technology. But the railway actually woke me up a little bit to see there was actually someone else that is a lot slower with adopting technology, and not for any other reason, but it's about safety, right? And how does that implement, and how does it improve the safety? How does it improve the flow and the process? And obviously, when you're starting to work with engineers, they're there to understand how would that affect the current process, and is there any advantage, disadvantage, or how does that provide the safety that we talk about? And obviously we usually get one always about the barrier timing and how long it's closed for, because they don't want to have that. Now there's just no way of getting around that when the barrier goes down and that or an object is detected, then you want to make sure that there is a train, if we can stop it and get that messaging back to the through the operations, that they can actually stop the train, then it's always better for. But so yeah, I think having that conversation with RISB as to how this can be implemented out into a bigger region, then that would be certainly welcome to have that conversation.
And we're always happy to have those conversations. I've got another question here. How does this technology compare to camera-based motion detection, whether pixel-based or infrared?
So I think it's all weather conditions. So I think that's the biggest difference. Doesn't matter about your lighting conditions or if you've got fog. We don't have that much fog in Australia, but yeah, it works in all weather conditions, I think, is the biggest winner there. Yeah.
Yep. Okay.
And the other thing
all
too
light
is,
conditions. Yeah.
yeah, and the other thing too is, I mean, if we take LiDAR, for example, I mean, as soon as a lens or something that may get scratched or damaged or blocked, from dust or something sitting on a lens, therefore then it becomes either partially inoperable or fully inoperable, or then the cost to then replace that, or you can't clean them. I mean, as soon as you start to try and clean a lens, it starts to get scratched, and there are issues with that as they go, and so they have to replace that.
Yeah, so there's a high maintenance cost.
There's no moving parts on the radar, no lenses.
Excellent. I'll ask a couple quick more questions. So can you interface with any current train control systems?
We do. I'm not 100%, would have to get back to that person with more information on that.
But you're currently interfacing with different train control systems around the world?
Yes.
No. Excellent. And one last question. There's a lot of opportunity for the data that is generated. You mentioned the sensor is only run during level crossing barriers down. There may be use cases for continuous monitoring, such as similar to CCTV. Is there a limitation to monitoring continuously? Is it things like high maintenance or large data requirements or things like that?
Yeah, so there's no limitation to monitoring continuously. And for the trial with Rio, that's exactly what we'll be doing. The limitation comes from like how much data you're storing. So especially with the CCTV that's paired with it for the diagnostics unit. But it's not too bad because you'll get a trigger and then you just go and check what the trigger was. You don't have to store all of the data for the whole time. So basically, I would just need to make sure we have 1 week's worth of data so that when there is a trigger, we can go and have a look at it.
Yeah. All right, thank you. Look, I'll ask one more quick one. What type of interface to signalling system is supported by this detection system? Is it data communication or a relay interface?
It's a relay interface.
Relay interface, right. Thank you very much. All right, well, look, I will call it there. So thank you very much to everyone who's joined us today for this very interesting discussion around risk reduction. Now, next week, sorry, not next week, but our next webinar will be on Tuesday, the 9th of December, starting at 12 o'clock Eastern States time. And this time we're going to look at implementing AS 7739 digital engineering. So it's one of our flag standards where we talk a lot about digital engineering. We're going to look at some cases on how you actually implement the digital engineering standard. That will be presented by Simon Vo. I look forward to seeing you all then, but until then, have a great and safe day, and we'll see you at our next webinar. Thank you very much.
Thank you.
Thanks, everyone. Yeah.